Okay, yeah, so I'd like to thank the organisers for inviting me to talk. So some people said they would like to hear about Spectra, so I'm giving you an introduction to Spectra. It's not intended to be like a really technically difficult talk. I am trying to sort of get you from not much knowledge up to a more sort of modern knowledge of what spectra are and how they work. So please do shout at me if you have any questions. And before I get started, you may be wondering, well, this is all sort of topology. Where's the algebra in this? That's a very reasonable question to have. There will be algebra, but it just will come late in the talk. Okay, so let's get started. Let me actually tell you what spectra are. So there we go. So very loosely, a spectrum is a bit like a topological space, but they're simplified in some manner. They sort of sit between spaces and chain complexes. So chain complexes are like linearized spaces, right? If I have a topological space, I can take its chains or cochains to get some sort of linearized version of it. And a spectrum is a sort of object that sits in between. So it's simpler than a topological space, and it's more algebraic than a topological space. So fitting in with today's theme, they control generalized cohomology theories. I'll say a little bit more about this later. I think, and a lot of actual topologists think, that they're interesting objects to study in their own right. And spectra are the base objects for spectral algebra. So again, I'll say more about this later. But loosely, you can think of a spectrum as being like a derived version of an abelian group. So in usual algebra, lots of objects are abelian groups with extra structure, right? A ring is an abelian group with some structure. A module is an abelian group with some structure. And in sort of spectral algebra, the base objects are spectra. So you talk about ring spectra, it's a spectrum with some extra structure, or module spectra, it's a spectrum with some extra structure. And if you like, you can also glue spectral algebra together and you get spectral geometry. I'll talk a little bit about that as well. Okay, so let's actually get going. There we go. So here's where I want to draw a picture. So if X is a topological space, you can form a suspension. So what is that? This is something denoted by sigma X. So I take X. That's not as nice as I want it to be, but that's fine. I take an X, I take a cone on it, I take another cone on it, and I glue them together. So it's two cones on X glued together at the base. One thing I want to say, in order to not lie to you, implicitly every space I'm going to talk about today is a pointed space, meaning it comes equipped with a base point. I'm going to really gloss over this because it's not very important. Of course, if X is pointed, well, the suspension isn't sort of naturally pointed. So here's a sort of base point on X. It has sort of images up in these copies of X, and to get the sort of pointed suspension or the reduced suspension, I have to collapse that vertical line down. But that's really unimportant. You should think of the suspension of X as being two cones on X glued together at the base. So this is a picture, if you think about it, that the suspension of the circle is the 2 sphere. And indeed, the suspension of Sn is Sn plus 1. Let me change my color back to a different color, maybe red. Okay. So why is homology or cohomology sort of easier to deal with the homotopy or the homotopy groups? Well, it's because you have suspension isomorphisms, right? If I have a space, there's a canonical suspension isomorphism between its nth cohomology and the n plus first cohomology of its suspension. And it's straight up not true that you have suspension isomorphisms for homotopy like this. So really, these isomorphisms here, these are what give you things. Oh, great. Okay, my page is reloaded. Well, while this reloads, I can keep talking. These are the things that really give you things like Myvie-Torres sequences and sort of good long exact sequence properties and make cohomology really computable. Whereas homotopy groups of space are famously hard to compute. You do have sort of a worse version of this. You do have suspension maps, they're just not isomorphisms for homotopy groups. So if I have a map from the n sphere to x, well, I can suspend it, suspension of the functor. I get a map from the n+1 sphere to the suspension of x, and this plays well with the homotopy relation. This descends to a map on homotopy groups. So this gives me a map from pi n of x, the nth homotopy group, to pi n+1 of its suspension. And really the core problem that makes homotopy theory more difficult than homology theory is this is not an isomorphism. Okay, let's move on to the next page. Now, in nice cases it is though. So this is the Freudenthal suspension theorem. I have a finite CW complex, so a CW complex with a finite number of cells total. What I can do is I can look at this big tower of suspension maps on homotopy, right? I'm allowed to do this. And in fact, the Freudenthal suspension theorem tells me that for a finite CW complexes, this tower eventually stabilizes. So in other words, if I go far enough along in the tower, these maps eventually become isomorphisms. So it's some sort of stabilization phenomena, stabilized under the suspension functor. You can be more explicit. I mean, if you have some connectivity estimates for x, you can get estimates for precisely when this stabilizes, but that's not important. So you might hope that if I take the colimit of this sequence, this stable homotopy group, you might hope that this is easier to understand than all of the sort of unstable ones. And indeed, this is true. They're still very difficult to understand, but they're just easier to understand than something which is extremely difficult. So I'll say more about this in a second once we see some examples. So I mean, you can play this construction generally, right? Nothing stopped me defining this stable homotopy group if I'm not a CW complex. So if X is any topological space, what can I do? I can look at the exact same tower I just wrote down, this tower over the homotopy groups of suspensions of X. And I can take its colimit and I call this thing the stable homotopy group of X, so the nth stable homotopy group of X. So I'm taking my limit over m of pi n plus m of the nth suspension. So n only appears once. It's an abelian group, right? Because higher homotopy groups are all abelian. And so this sequence has like a tail of abelian groups. So it's always some abelian group. And if X is something like a CW complex with maybe finitely many cells in each degree, then it's always going to be finitely generated as well. Okay, so this is what the stable homotopy group is of a space. And well, you can see pretty easily that if X and Y are stably equivalent, which is to say, I take R suspensions of X and I get something that's weakly equivalent to R suspensions of Y, then their stable homotopy groups must agree. This is pretty clear from the definition. And so I want to regard two spaces that are stably equivalent as being the same, or the stable homotopy groups see them as being the same space. So what's the basic idea behind Spectra? The idea is that there should be some category of space-like objects, spectra, where you can invert sigma. So if sigma r of x is sigma r of y, then x should actually be equal to y in some sense. And there's some notion of weak equivalences which are detected by stable homotopy groups. So I want to say that two things are stably equivalent, they have the same stable homotopy groups. And of course, if there's a map between them inducing that isomorphism. And this is precisely what spectra are. So spectra are designed to be objects that capture stable phenomena in algebraic topology. Whereby stable, again, I mean stable under the suspension functor sigma. Okay. Any quick questions about this just before I actually tell you what spectra properly are? Okay, let's move on. So yeah, let me actually tell you what spectra properly are. So what is a spectrum? It's an n-graded sequence of spaces, xi, one for each non-negative integer. together with some structure maps from the suspension of xi to xi plus 1. So the idea is that suspension increases the degree. And then what's the morphism of spectra? Well, it is what you think it is. It's a sequence of maps, one for each I, xi to yi, making the obvious diagrams commute. So I can look at a commutative square, suspension of xi to xi plus 1, suspension of y to y plus 1, and I want this square to commute. So it is just what you think it is. Okay, so this defines a perfectly good category of spectra. So spectra are objects which have homotopy groups. They do have homotopy groups. So if I start off with pi n of xi, well, what can I do? I can use the suspension isomorphism on homotopy, let's call that sigma, to get a map to the n plus first homotopy group of the suspension of xi. And then what can I do? I can take pi n plus 1 of my structure map of spectra, and this gives me a map to pi n plus 1 of xi plus 1. And so overall, what can I do? I get a big tower or a big system of abelian groups, mostly abelian groups, pi n plus m of xm, and I set the nth homotopy group of x, so this is the nth homotopy group. I set the nth homotopy group of x to just be the colimit of this tower. Okay, so spectra have homotopy groups. Now let's see some examples. Here's the time where we can finally see some examples. So let's suppose X is any topological space. Then you can cook up a suspension spectrum, sigma infinity of X. Well, what is it? At level I take the ith iterated suspension of X. And then what are my structure maps? I need a map from the suspension of the ith iterated suspension to the I plus first iterated suspension. That map's just going to be the identity. And it's pretty easy to see from this definition that the nth homotopy group of the spectrum, sigma infinity X, is the nth stable homotopy group of the space I started with. Okay, so this gives me some sort of embedding of spaces into spectra. Okay, so let's say an actual concrete example. This S, blackboard bold S, this is the sphere spectrum. It's the suspension spectrum of S0, the zero sphere. You'll recall from earlier that if I suspend Sn, I get Sn plus 1. So if I suspend S0 I many times, I get Si. So the ith level of the sphere spectrum is just a copy of the I sphere. This is why it's called the sphere spectrum. Now, what are the homotopy groups of this guy? The homotopy groups of the sphere spectrum are precisely the stable homotopy groups of spheres. Now, you've probably heard about these because they are absolutely difficult to compute. I mean, we know what they are up to about dimension somewhere between 60 and 100, I think. But there's no good pattern to them. So even for this very simple sort of space built out of spheres in a very simple way, its stable homotopy groups are absolutely intractable. So spectra are very hard to do computations with as a rule. Okay, let's see some more examples. Okay, so we saw just now that space is embedded into spectra. And in fact, abelian groups also embed into spectra. So if I take any abelian group A, I can cook up something called an IslandbergMaclean spectrum, HA. Now, what is this? It's if you know what an Islandberg-MacLean space is, it's built out of Islandberg-MacLean spaces in some sort of reasonable way. If you don't know what an Islandberg-MacLean space is, it's not important, so don't worry. But the point is that the ith level of this spectrum is something that we understand. And the point of this Islandberg-MacLean spectrum is that its homotopy groups, what are they? Well, in degree 0, I get the group I started with. and otherwise I get 0. So if you want to think of spectra as being a little bit like chain complexes, this is the analog of the chain complex that is A placed in degree 0 with no differentials. Yeah, so this gives you a sort of embedding of abelian groups into spectra. More generally, you can indeed play this game with chain complexes. If A is a chain complex of abelian groups, there's a similar construction you can make of an Eilenberg-MacLean spectrum, or maybe some people call this a generalized Eilenberg-MacLean spectrum, with the homotopy groups of HA are precisely the homology groups of A. Now, one important thing to note here is that I didn't make any connectivity assumptions on A. So A is allowed to have lots of negative homology. So my spectrum HA is allowed to have negative homotopy groups. So this isn't a phenomenon you see when you're working with spaces. But when you work with spectra, because you're allowed to sort of suspend and desuspend things at will, you can get negative homotopy groups. So spectra are more like sort of unbounded chain complexes. In fact, there's a strong sense in which spectra are like a sort of non-linear version of the category of unbounded chain complexes. Maybe I'll say a bit more about that later. But if I forget, you can always ask me. Okay, so chain complexes of abelian groups embed into spectra is the point. Okay, so now what can we do? Well, we can try to invert some notion of weak equivalences between spectra. So I say that a map of spectra is a stable equivalence if it induces an isomorphism on homotopy groups, so on stable homotopy groups. So for example, if I have two spaces which are weakly homotopy equivalent, their suspension spectra are definitely stably equivalent because their stable homotopy groups contain sort of less information than their usual homotopy groups. But more to the point, spaces that are not weakly homotopy equivalent may become stably equivalent when I think of them as spectra, because stably their homotopy information is the same. Okay, so that's what a stable equivalence is. And now what can I do? Well, I can now form something called the stable homotopy category. This is called SHC. This is the localization of spectra at the stable equivalences. In other words, I take the category of spectra and I just formally invert all of the stable equivalences. So every stable equivalence I have, I just throw in a formal inverse. So this thing is a little bit wild. It's hard to have control over. It's formally the same thing I do as when I form like the derived category of a ring, right? If I have a ring, how do I form its derived category? I take its category of chain complexes and I just formally invert the quasi-isomorphisms between them. So again, if I think of spectra as nonlinear chain complexes, the stable homotopy category is going to be like some sort of nonlinear derived category. In fact, this is really true on some quite strong levels. So you'll remember we had this Eilenberg-MacLean spectrum construction, which takes an abelian group and outputs a spectrum, or even a chain complex of abelian groups and outputs a spectrum. This is homotopically well defined. This sends weak equivalences to weak equivalences, and so this actually gives me a functor from the derived category of an abelian group. The derived category of abelian groups to the stable homotopy category. And in fact, it's an embedding. So the derived category of abelian groups actually lives inside the stable homotopy category. This is one of the senses in which spectra are quite algebraic objects. In fact, the stable homotopy category is triangulated. If you don't know what a triangulated category is, it's a little bit like an abelian category. You've got some notion of exact sequences. It's a triangulated category, and this inclusion here is a triangle functor. meaning that it preserves the exact triangles. Okay, so there's a lot of structure on this embedding, is the point. Okay, let's move on. As you would want to happen, if you look at the stable homotopy category, the suspension functor becomes invertible. So I can not only suspend spaces, I can desuspend spaces by taking sigma inverse. Equivalently, I can actually just take their loop space. So you'll recall sort of for actual topological spaces, the suspension functor is left adjunct to the loop space functor. So this loop space functor omega, I take the space of loops in my space, so like pointed maps from S1 to my space. And in fact, when you think of it like this, it's a sort of Hom tensor adjunction. Yeah, so this omega functor actually belongs to spectra. So I can take the loop space of a spectra, and when I go down to the stable homotopy category, the thing that models the desuspension is the loop space, maybe up to a grading shift. But the point is, you can desuspend things, right? I can take negative suspensions of my objects. So in particular, the stable homotopy category has a collection of spheres. So sort of, I take the sphere spectrum and I can suspend it up. This still looks like a space, right? Like a topological space. But I can also suspend it downwards. So I get sort of negative dimensional spheres. And these are that represent the negative dimensional homotopy groups. So to make what I just said precise, the stable homotopy category is enriched in abelian groups. So if I take two spectra and I look at the set of maps between them up to homotopy, up to stable homotopy equivalence, I get an abelian group. So I can add morphisms. I have zero morphisms. I can subtract morphisms as well. And in fact, so that notation is this square brackets notation I've got here, right? So if I have two spectra, x and y, I write x square brackets y to mean Hom in the stable homotopy category from x to y. And then, yeah, the point is that these spheres represent homotopy in the sense that in the stable homotopy category, the space of maps or the group of maps from the ith suspension of the sphere spectrum to x is precisely the ith homotopy group of x. And this is the sort of thing you might expect given what happens for topological spaces, right? If I have a topological space X, then its ith homotopy group, at least for I positive, is just the space of homotopy classes of maps from the I sphere to X. Equivalently, this is the space of homotopy classes of maps from the ith suspension of the zero sphere to X. So this is just a reflection of what's going on for usable topological space. Okay. So here's a maybe more technical remark for people that know about homotopy theory. All this enhances to model structures. So I don't want to tell you what a model structure is, but it's essentially a gadget that allows you to invert weak equivalences in a controlled and sensible manner. Because if I just sort of take any category and any set of weak equivalences and try to invert them, I may have some set theoretic problems. I may have some other problems too, just in having control over this quotient or this localization rather. And a model structure is one thing that allows me to do that. So if you know what a model structure is, the stable equivalences are indeed the weak equivalences of a model structure. The fibrant objects are something called the omega spectra. So if I look at the structure maps of a spectrum, sigma xi to xi plus 1, These are just spaces now. So I told you a second ago that loops are adjoint to suspension. So a map like this is the same as a map like this. It's supposed to be an omega, doesn't look like it. That's also supposed to be an I. And I'm an omega spectra precisely if this adjoint map is a weak equivalence. So all suspension spectra are omega spectra. This is easy to see if you unravel the definition. So those are the founded objects, and the co-founded objects are harder to describe. Their CW spectra are in particular all cofibrant. So a CW spectrum is one where each level xi is a CW complex, and my structure map xi to xi plus 1 is an inclusion of CW complexes. So it's a cellular map, in other words. Okay, so that was a technical remark. You don't need to know about model categories. I might mention omega spectra again later. Okay. So while my iPad is reloading the page, maybe now is a good time to ask if anyone has any questions.
Yes, I think I have a question. So these negative spheres, so we can just consider them as sort of in loop spaces of then the point, and then the loop space of the point of the loop space.
Yeah, more or less. You have to impose a grading shift as well, which I didn't really tell you about. So there's a up on the actual category spectra. There's a suspension functor and a loop space functor, and their adjoints. And there are also grading shift functors. I can shift left and just sort of chop off some of my space, or I can shift right and I can just pad it with points. And no, go on.
And do they behave as nicely as you know the spheres that we know? Like they go up each dimension. Are they also going like?
Yeah, I mean, there's not really a good notion of dimension for spectra. Is the problem?
Okay.
Because I think, sort of by any sensible notion, any spectrum is infinite dimensional. I mean,
right. Yeah.
If I ask what's the dimension of the sphere spectrum, it doesn't quite make sense to ask that, right? Because the different graded components all have different dimensions.
No, sure, but I meant like component-wise, maybe, or right. No, now I get it. Like the negative spheres will be spectra rather than.
Yeah, they're spectra.
Right,
They're not
yeah.
suspension spectra of spaces. Yeah.
Yeah. Okay.
Because a suspension spectrum of space always has connective homotopy. Always, the homotopy is always concentrated in positive or non-negative degrees.
Right. Okay.
But these guys, by construction, have negative homotopy groups. So
right.
they're not immediately constructible as suspension spectra of spaces. Yeah.
Okay. Cool. Okay. Cool. Thanks.
My point about loop spaces is that up on the category spectra, loop space and sort of inverse grading shift are not the same, but down in the stable homotopy category, they do become the same. So if I've got a sufficiently connected spectrum, I can take its loop space. That's still like a suspension spectrum, and that represents the shift leftwards, I guess. But yeah, if I've got something which has non-trivial pi naught, then its desuspension is not going to be represented by a suspension spectrum of the space. Yeah.
Okay, I will think more about this.
Yeah, feel free to ask again later. Yeah. Any other questions before I continue? Okay. Yeah. So I want to very briefly tell you about cohomology theories, given the title of the session today. So what is a cohomology theory? It's a functor that takes connected CW complexes as input and returns a graded abelian group as an output. Sorry, I haven't got my pen. So, of course, the prototypical example you want to keep in mind is singular cohomology, right, with Z coefficients. So, why do I restrict to connected CW complexes? It's not immediately obvious why I want to do that. I will tell you soon why I want to do that. And of course, the cohomology theory has to satisfy some extra conditions. It has to satisfy homotopy invariance. So if two CW complexes are homotopy invariant, I get the same graded abelian group. It has to send wedges to products. So I can take wedge sums, which are sort of, if I have a space X and a space Y and they're both pointed, I can just glue them together at the base point. So that's what the wedge sum is. And I want F to take wedge sums to products. And if I have a CW pair, I want some sort of long exact sequence in cohomology, which I won't write down, but yeah, it's like a Mayer-Vittorius sequence. Okay. And why am I telling you about cohomology theories? Oh yeah, so let me show you some examples. So if R is any commutative ring, singular cohomology is a cohomology theory. That's good. That's what we want. Complex or real K theory. So using complex vector bundles or real vector bundles on my space is an example of a cohomology theory. There's a cobordism cohomology theory, which maybe I don't want to say too much about right now. And there are many more examples. Okay. And one of the original motivations to introduce spectra was because they are objects that control generalized cohomology theories. So this is something called the Browne representability theorem. This tells you that all cohomology theories are indeed representable by spectra. So in other words, F star of X, so remember it's a graded abelian group. If I have any cohomology theory F, I can cook up a spectrum E such that my value of F on X is the set of the abelian group of homotopy classes of maps from the suspension spectrum of X to E. And just to note, where does the grading come from? Well, the grading comes because I can suspend and desuspend, right? I say that the ith graded component of this guy is what I get when I desuspend this guy I many times. So if you like, you can think of the stable homotopy category as being enriched not just in abelian groups, but actually in graded abelian groups. And they retain all the information about these shifts. Just like the derived category of a ring, I can either think of it as being over abelian groups, like x0, or I can think of it as being enriched over graded abelian groups. I can take the whole X algebra. Okay, so that's the Browne representability there. And why did I make these stipulations earlier that I had to work with connected CW complexes? Simply because it's false if I don't. If I drop connectivity, then the Browne representability. If I drop connectivity, the Browne representability theorem isn't true. If I drop the stipulation that my spaces are pointed, it's also not true. So this is secretly why I wanted to talk about pointed spaces, or it's one of the reasons why anyway. The CW bit is less important. It just allows me to state. It allows me to have a notion of CW pairs for my long exact sequences. So it's unclear that you would want to get rid of that anyway. Okay, so spectra control cohomology theories. I just wanted to say that briefly before I get back onto different aspects of spectra. And yeah, so even better is that this association of cohomology theory to spectra is functorial in an appropriate sense. maps between cohomology theories lift to maps between spectra. Now, it's not true that a cohomology theory is the same thing as a spectrum. There may be sort of maps between spectra that are zero on cohomology theories, but it's a pretty good dictionary still. So as an example, singular cohomology with coefficients in a ring R. This is co-represented by the Islandberg-MacLean spectrum HR that we saw earlier. K-theory, so complex K-theory is represented by something called KU, real K-theory is represented by something called KO, cobordism is represented by some sort of spectrum called MO. I won't bother talking about cobordism. Another example of a spectrum that we of course know is the sphere spectrum. You might ask, what cohomology theory does this represent? It's something called stable cohomotopy, which I think some people do think about. So let's I think move on from cohomology theories. Okay, so let's recall I'm working with pointed spaces, right? So these pointed spaces have something called a smash product. So what is it? I can take the usual Cartesian product of x and y. This, of course, fails to be pointed. There's no natural choice of base point because it contains sort of pictorially, it contains like a copy of x cross the base point of y and a copy of the base point of y cross x. And I want to collapse these down. And that's precisely what I do. I take the smash product and I quotient that by the wedge product. Now the wedge product is, it really is x cross the base point of y, union y cross the base point of x, where I identify the two base points now. And so for example, if I smash two spheres together, if I smash an M sphere and an N sphere, I get an M plus N sphere. So it behaves well with respect to spheres. Whereas, you know, if I take the product of two copies of S1, I get a torus, which is definitely not an S2. But then the point is that I want to collapse down the fibers above the base point. Well, generally, so the suspension functor is actually the smash with S1 functor. So if you haven't seen this before, this is a nice little exercise to think about if you get bored later, or indeed even in the talk. So this is a nice thing to think about. This is a nice little exercise to do. Now the problem is, you might want to lift this smash product to spectra, and you might want to lift it to spectra in a homotopically sensible way. I don't want to make precise what I mean by homotopically sensible, but in a way that interacts well with the weak equivalences, with the stable equivalences. And unfortunately, this isn't possible. This is a theorem of Gauntz-Lewis from a while ago. I don't know precisely when, I think maybe the 80s, maybe even the 70s. And sort of loosely, why is this? Well, it's because spheres have some sort of non-trivial braiding, right? If I look at S2, which is S1 smash S1, I have some sort of automorphism of it induced by the braiding automorphism S1 smash S1 to S1 smash S1, but where I beat the factors. So this is like a flip or a twist. And this braiding automorphism, you can check, this is non-trivial, these induce non-trivial automorphisms on the homotopy groups. So the above braiding automorphism of S2 I've written down there. This is -1 in pi2 of S2. And if you try to just sort of naively write down what a smash product of spectra should be, you find that at some point you want to use these braiding automorphisms, but of course you run into problems because then by acting by these, you're changing the homotopy type around, and we don't want that to happen. The problem is even worse with higher dimensional spheres, right? Sn is a n-fold smash product of S1s, and this gets an action of the symmetric group via permuting all the factors. So the problem only gets worse as you go up in dimension. Okay, so one way to fix this is to add more structure to my spectra. And what I can do is I can just carry around an action of a symmetric group on each level of my spectrum. And I can remember this. And then if I'm remembering things like these braiding automorphisms, basically the problem goes away. So let me just at least define for you what a symmetric spectrum is. So a symmetric spectrum is more or less the thing I just said. It's something where you carry around an action of the symmetric group on each level of your spectrum. So a symmetric spectrum is a spectrum, so a collection of spaces xi, together with structure maps, where I have an action of the ith symmetric group on my ith space, my ith level. Now what I can do is I can write down composite maps. I can go not just from S1 smash xi to xi plus 1, but I can go from sk smash xi to xi plus k. And I demand that these composite maps are all equivariant with respect to the action of sigma k cross sigma I. So it's not clear what this action is. Let me just tell you. Sk has a sigma k action. We just saw that. Xi has a sigma I action. Well, that's built into the definition. So their smash product gets an action of the product. Now, xi plus k has an action of sigma I plus k. And, well, if I have an action of sigma I plus k, how do I get an action of sigma k cross sigma I? Well, I can just include, right? If I'm permuting k things around, and then next to it I'm permuting I things around, I can regard this as a permutation of k plus I things. So that's what a symmetric spectrum is. Now, I don't want to get into the technicalities of how to define a smash product for symmetric spectra, but I will say that it can be done. Sorry, I'm trying to, there we go. This is probably the most technical part of the talk. So the category of symmetric spectra does admit a symmetric monoidal smash product. And this is essentially because, yeah, these problems with braidings go because I've remembered my symmetric group actions. The actual construction is a little bit more technical. If you're interested, you can ask me at the end, but I don't want to write it down right now. And the unit for this smash product is the sphere spectrum. Well, this isn't maybe too surprising if you think about it. Sn smash a space is the n times iterated suspension. So effectively, what am I doing when I smash something with S? I'm just sort of, well, I'm shifting things up in a degree, but that was when I started with something that lived in that degree anyway. So I'm not really doing anything. Okay, this wasn't really a very good explanation, but hopefully you have a vague idea of why that's true. So the unit is the sphere spectrum. That's what's important. Just like S0 is the unit for the smash product, and it's reasonable to believe that if I take the suspension spectrum of a product, I get the product of the suspension spectrum. That's maybe a better way of thinking about it. Okay, so the point is there is some kind of smash product on this category of symmetric spectra, so spectra with some extra data on top. And I should think of this as being like the category of abelian groups with the tensor product. So what is a ring? It's an abelian group together with a monoid structure with respect to the tensor product. So it's an abelian group A with a map A tensor A to A satisfying some identities, right? saying that the composition has to be associative, there has to be a unit, that sort of thing. So I can play this game in any category where I have a symmetric monoidal product. So I can define a ring spectrum to be precisely a monoid for this smash product. So more concretely, it's a spectrum A together with a pair of maps, A smash A to A, and a map from S to A, satisfying some identities for associativity and units. That's really all a ring spectrum is. And I mean, these axioms are they don't take you long to write down, right? There are not many of them. You can write them down explicitly. So I think of this first one as being the multiplication, and I think of this second one as being the inclusion of the unit 1. Okay, so that's what a ring spectrum is. So as an example, the sphere spectrum is the initial ring spectrum. So that's why people use blackboard bold S for this. It's with analogy with the blackboard bold Z for the initial ring. So every ring spectrum receives a unique map from S. If A is a ring, then the Eilenberg-MacLean spectrum HA is indeed a ring spectrum. So it inherits the multiplication from A. Okay, and if you think about cohomology with coefficients in A, this is a ring, right? You have cut products on cohomology, and somehow the multiplication structure here is really induced from the multiplication structure on HA. Okay. Once I have rings, I can talk about modules. So a module over a ring spectrum R is a spectrum M together with some action map R smash M to M. Again, satisfying some obvious identities. So it's just like a usual module over a usual ring. As an example of this, every spectrum is an S module in a unique way. The uniqueness is related to S being the unit, and it's equivalent to S being the initial ring spectrum. So if I didn't like the word spectrum, I could equivalently use the word S module. Or perhaps if I wanted to think of spectra as being more algebraic objects, I'd refer to them as S modules. So now we're really getting quite algebraic, right? We've got sort of ring objects and we've got module objects, and we can now try and do algebra with these things. Yeah, so how does this Eilenberg-MacLean functor actually interact with the algebra? So it's true that up to homotopy, I'm being a bit vague about this, up to a notion of homotopy, modules over HR, which is a ring spectrum, so R is a ring now, HR is a ring spectrum. A module over HR is the same thing as just a module over my ring R. Well, a DG module, right? So a chain complex of modules. The derived category of R is equivalent to the homotopy category of HR modules. Well, and by sort of base change, right, I have a map from S to HR. Ooh, that was supposed to be an arrow, but it's not an arrow. I have a map from S to HR, right, because S is the initial ring spectrum. And so I can base change an HR module back along this map to get an S module. And in fact, on homotopy categories, this gives me an inclusion of the homotopy category of HR modules into the homotopy category of S modules. And well, an S module is just a spectrum, so the homotopy category of S modules is precisely the stable homotopy category. And this composite map is precisely the one we saw earlier. Okay, great. So the stable homotopy category contains the derived category of modules over every ring inside of it, in a way that interacts well with the algebraic structure. Let's skip that. If you're really interested in homotopy theory of symmetric spectra, you can ask me at the end. I want to just briefly say that there are other models you can use. So instead of having an action of the symmetric group on each level, I can ask for an action of the orthogonal group. That's fine. These things are called orthogonal spectra. There are various other models that are a little more complicated to describe. There are things called S modules, which is sort of historically the earliest approach to highly structured spectra. you can think about things just in an extremely functorial way. These are things called excisive functors. Sometimes it's useful to have coordinate-free spectra. So instead of my indices being the natural numbers, I index by finite dimensional real inner product spaces. It's sometimes useful to do these kind of things, but symmetric spectra for me probably my favorite model because they're the most algebraic and because they're the simplest. I mean, these latter three models require some work to set up. I mean, symmetric spectra requires a lot of homotopy theory to set up, but as little topology as possible. Okay, so let me briefly finish by talking about some of the applications of ring spectrum and some of the things I've been thinking about recently. Well, first up, what are the applications of rings, right? I mean, what do we like to use rings to do? Well, the first thing we like to use commutative rings to do is do algebraic geometry, right? I mean, algebraic geometry is locally modeled by commutative rings. So the affine objects in algebraic geometry are exactly commutative rings. And then modules, in this picture, modules correspond to sheaves. One other thing we like to do with rings is we like to do homological algebra. So you don't need to be commutative anymore. But in particular, we like to, you can compute things like tor and ext. And in particular, you can do things like Hochschild theory. Which again, I'll say a bit more about in a second. So these are two nice applications of rings. And you can make these theories work if you input ring spectra instead of rings. So let me briefly say something about spectral geometry. Guess I've gone through it. So yeah, very briefly, I don't want to really say anything much about spectral geometry in particular. But usual algebraic geometry is, as I said, modeled on commutative rings, right? Your affines are commutative rings. If you're familiar with derived geometry, derived algebraic geometry, the affines here are they're commutative DGAs, at least if you're in characteristic 0, or more generally, they're commutative simplicial rings. And the point of derived geometry is it's some sort of enhancement of classical algebraic geometry that takes into account sort of higher homological information, and so takes into account sort of information about intersections that aren't transverse, things like that. What I can do is I can play the same game with commutative ring spectra, and if I sort of glue these together in an appropriate way, I get the theory of spectral algebraic geometry. So this is again something that has more objects than derived geometry. Now, why? Sorry, that was supposed to be like an inclusion sign, but it didn't really come off. So why might I want to do this? I mean, at the moment, a lot of the applications of spectral geometry are topological. I'm not actually aware of good geometric applications of spectral geometry. But also people haven't been studying it for very long, and the people that study it are algebraic topologists, so they're a bit biased already in what they're interested in. So there's been some applications towards something called topological modular forms, which I don't want to talk about. I probably shouldn't anyway. But yeah, the point is that one use of ring spectra is you can do a general form of algebraic geometry with them. Okay, so very finally, what I want to talk about is a more algebraic use of ring spectra and module spectra. If I have a ring spectrum A and I take two A modules, N and M, I have X groups and I have Tor groups via the usual sort of construction. So one way of thinking about this is that the smash product passes to the stable homotopy category as a sort of derived smash product. And the tors between N and M are the homotopy of this derived smash product. Similarly, I have sort of mapping spectra. So I have not just complexes of abelian groups between spectra, but I have sort of actual mapping spectra between two spectra. And there's a sort of derived mapping spectrum construction that lives on the level of the stable homotopy category, and the X spectrum, or the X algebra is the the X great abelian group, I guess, is the homotopy of this derived mapping spectrum. So I went through that very quickly, but they're essentially constructed via the usual sort of way you know from homological algebra. In particular, you can do Hochschild theory. So I don't really want to talk about what classical Hochschild theory is, mainly because I don't really have time. But let me just tell you how to do topological Hochschild theory. So if R is any commutative ring spectrum and A is any R module, I can cook up something called its derived enveloping algebra, which I denote by A upper E lower R. This is I take A and I smash it with its opposite algebra over my base R. Okay, so what are some examples of this? If R and A are actually just discrete rings, so usual rings, then its derived enveloping algebra is the derived tensor product of A with its opposite over my base ring. So if R is a field, this is the usual tensor product, for example. A really boring example is if I take the derived enveloping algebra of R relative to itself, I just get R back. Well, actually, maybe I get an R op back if I care about the algebra structure. It's true that if I take the rational numbers Q and I look at their derived enveloping algebra over the sphere spectrum, I get the rationals back. This is to do with there being no interesting torsion-free elements in the stable homotopy groups of spheres. However, there are lots of interesting torsion elements in the stable homotopy groups of spheres. And so if I take Z mod P, if I take the derived enveloping algebra of this guy over the sphere spectrum, this is a very large ring. Yeah, the homotopy of this ring is the dual Steenrod algebra, which is like a polynomial ring on infinitely many generators. So it's very big. And then, well, what's the point? The topological Hochschild homology of A relative to R. Well, what do? I define it to be the Tor over the enveloping algebra from A to itself. And I also have a notion of topological Hochschild cohomology, which is X over the enveloping algebra from A to itself. Now I should stop, so I will just say that lots of people have thought about topological Hochschild homology because it's very closely related to algebraic K theory. There's a lot of literature on this. Not many people have thought about topological Hochschild cohomology. It's related to a sort of nonlinear deformation theory of rings, and it's what I've been thinking about recently. So I will stop there.